All right, we'll get started in a few minutes here. We're doing, I would say, is the tough stuff on the midterm. We'll get started in a few minutes here, which is Castle Learnings 2 and 3. If you have any questions, just send them out on Remind, and that's it. So just hang tight. Those of you that start logging in, if you remember from yesterday, we've just got to give it a few minutes so people can get this up and going. We'll be doing atomic structure. We'll be doing bonding, drawing ions, drawing Lewis dot structures, all that fun stuff. Properties of compounds, whatever we can get through. Hoping for this to last a little bit longer than an hour tonight, maybe. We'll see what happens, but we'll get started in a couple minutes. Hopefully your math midterms went okay today. I know Algebra 2 can be a bit of a pain, but I've heard good things. My geometry students, hopefully you didn't have a hard proof or two. I don't know how many proofs they give you, but hopefully it went okay. Thank you. Whoever texted me, you know who you are. Thank you. I like it too. It's a edible arrangements mug. It's nice. It's big. It holds a lot of liquid, and yeah, we have a lot of mugs. So, getting a lot of texts, so I'm assuming we have more people tonight. Feel free to share this with your friends if you want. My first video got more views than I have students, so I'm going to assume that you shared it with your friends, unless some of you watched it more than once. But this is just not for my students. Other people can join. And it's 7:30, and I know some people will be a little late, but that's okay. They can always ask questions at any time. So, yesterday, I'm trying to remember where we left off. I know on here, I definitely want to go over number 4. I don't remember if we did number 1, but we'll do 4, because I've gotten a lot of questions about excited and ground state, general questions pertaining to this specific one, stuff like that. So let's kind of unpack what excited means. So if you look up the periodic table for calcium, and you find its electron configuration, you'll see that calcium is 2882. And we call that the ground state. All those electrons are in the ground state, the natural state of where calcium's electrons want to be. So in calcium's natural atomic state, you have 2 electrons in the first energy level. Let me make this thinner. 2 electrons in the first energy level, 8 electrons in the second, 8 electrons in the third, and then 2 electrons in the fourth. So each of those notches means a different energy level. And when we say energy level, I mean, if you think about like the Bohr model of the atom, you have the nucleus in the middle, and then your electrons get further and further and further away. So each one of those circles, for my math people out there, each one of these concentric circles, math term, is a different energy level. So for calcium, naturally, its ground state is 2882. So obviously the excited state can't be answer choice 4. And when we say an atom becomes excited, it's not gaining electrons, it's not moving electrons. The electrons are just gaining energy and moving from any lower energy level to any higher energy level. So there's numerous correct answers for what a possible excited state could be. But either way, you're not gaining or losing electrons. So if I count up calcium's electrons here, I have 20. The correct answer must also have 20. Because again, the electrons aren't leaving. You're not gaining, you're not losing. They're just moving. And the only answer choice that even still adds up to 20 is 3. And if you look at answer choice 3, electrons in the third energy level moved to the fourth energy level. Now we call that excited. The electron has gained energy. Each energy level that you go further and further and further away, so if we imagine we have this Bohr model again, each electron as you go further and further and further away has more energy. So the second energy level has more energy than the first, and the third energy level has more energy than the second, etc., etc. So every time they move further and further away, you're gaining energy and you're becoming excited. So the right answer for this one was 3. Those of you that are joining us for the first time, you'll notice my Castle Learning questions, for whatever reason, are out of order from yours, even though I didn't select randomize. I apologize. That's not my intention. It's still okay. You can still go over it and see the right answers and always go back and plug them in later. I got a question that was, how much of the second Castle Learning are we going to go over? Not as many as we did last night. So I'd like to get to the third one by 8 or sooner, because the third one, in my opinion, is the hardest one. So I'm going to tackle a bunch of questions with this excited and ground state stuff. I'll tackle a couple questions dealing with atomic structure, and I'm just going to move forward. But text me on Remind if you have any questions. 6 is another ground state, excited state question. So when you see 6, when an atom in the excited state goes back down to the ground state, let's keep in mind what we just talked about. The electrons are not changing. So 3 and 4 are wrong. When it got excited, it gained energy. You input some form of energy, whether that be light or fire or whatever, and it gained energy to move up from the first to the second or the second to the third. So when those excited electrons move back down from wherever to wherever, if you're going this way, you're losing energy. And the word that they like to use is emit, because you'll typically see it in the form of light. So that's a big short answer question that pops up from time to time. So when you go from excited back down to ground, light is emitted, or energy is released. Something that along those lines. Just keep in mind that it's the electrons that are doing this. So don't say it. Try to avoid saying it on short answer questions as much as you can, because you have to be clear with what you're talking about. How many questions are on the test? It is 40 multiple choice. There'll be 2 points each, and then 12 short answer, each totaling up to 15 points. So a couple of short answer are worth 2 points, but most of them are worth 1 point. So the test is out of 95. Number 9. We'll do 8 and 9. Nucleus of an atom. Anytime you see nucleus, go back up to our model. We know the electrons are out here orbiting around the nucleus, which means in the nucleus must be the other two things, which are protons and neutrons. The other term that pops up a lot is nuclear charge. Nuclear charge. When you see this term nuclear charge, that's just a fancy word for protons. Because it wants to know the charge of the nucleus, and the only thing charged in the nucleus are protons. So, to revisit that, protons are positive. Protons weigh 1. So protons have a mass and they have a charge. Neutrons have no charge, but also weigh 1. So neutrons are neutral, but have a mass. So these two right here is how you get your mass. And you simply just add them together. So if you're given atomic mass, subtract the protons from the mass, minus protons, and you will get neutrons. All right, so mass minus protons, and you will get your neutrons. Just to review that. The next question goes over another topic that I went over with a couple of students today. What is the number of electrons in a potassium atom? Atom. And we're still getting a little confused on the difference between an atom and an ion. So atom equals no charge. And an ion has a charge. So if it asks you how many electrons are in the potassium atom, go to your periodic table, find potassium, which is K, not P. No, that's phosphorus. Again, those of you that didn't join us yesterday, if you don't remember, look it up. All the symbols and their names are given to you. Don't make a silly mistake saying K is P and P is K, or nitrogen is Ni, which is nickel. Nitrogen is N. Be careful. Okay? So, if it says potassium atom, you find K, you find its atomic number, which is protons. Don't forget you have a key here that kind of tells you what everything is. Not necessarily what they mean, but in general, this is the atomic number, etc. Find potassium's atomic number, which is 19. So we know potassium has 19 protons. And if it says atom, that also means you have 19 electrons, because atoms have no charge. That doesn't mean no electrons. That means they cancel each other out. So your positive 19 protons and your negative 19 electrons cancel out. You get 0. So how many electrons does potassium have? 19. Another trick, which I don't really like, but you could technically do this. Look at potassium's electron configuration and add it up, because those are electrons. And if you add that up, guess what you get? 19. So, when do we use charges? There's two instances. One of them I'll talk about right now. The other one I'll talk about later. The only time you should use a charge is when you see the word ion, or I tell you it's charged, or something in the question gives you a hint that it's charged. Never use it for atoms. The second instance comes up in the other Castle learning, hopefully, which is bonding. That's when you check the charges and crisscross and all that stuff. Let's see. Wave mechanical model. That's Schrodinger. They almost never use his name. Wave mechanical model, typically what they're going to talk about are orbitals. And electrons are in orbitals. Not orbits, orbitals. So when you see that word orbital, your mind should go to probable location of electrons. Because that's what orbital means. So electrons aren't going around the nucleus like this. That's outdated, that's technically wrong. That was the Bohr model. We use that model because it's easy to conceptualize, it's easy to draw, but that's what it is. It's just a model. It doesn't have to be correct. This model is more accurate than that model. But all you really need to know about orbitals is that they exist, and that's where the electrons are. 17. So that's the one that popped up with ions. And I'm trying to think if this was the one that was requested. Someone requested Ca+2 electron configuration isotopes. We'll get to isotopes. So this is what I'm talking about when I say the problem needs to mention the word ion. That's when the charges matter. And that's when you have to take a step back and say to yourself, what do I have that's positively charged? What do I have that's negatively charged? And what does that mean? So you have two things in any atom that are always charged. You have protons, which are positive, and electrons, which are negative. If you look up aluminum on the reference table, you will see that aluminum's atomic number is 13. So any aluminum, I don't care if it's an atom, I don't care if it's an ion, I don't care what it is, if you have aluminum, you know that the protons are 13. So you have 13 positively charged things. So if you see Al plus 3, don't think that that means you've gained 3 electrons, because you haven't. Because if your charge is overall positive, then you need to have more positives than you do negatives. And in this case, I have 3 more positives than I do negatives. It tells you right there. You have 3 extra positives, so that means you should have 3 more protons than you do electrons. So in this case, you have 10. And we can do another quick example with a negative ion. Let's say you had O2 minus. You look up its protons and it's 8. It tells you you have 2 more negatives than normal. You have 2 more negatives than you do positives. So in this case, your electrons should be greater than your protons. Never change the protons. You change the protons, you change the element, and you'll get it wrong. Okay, there was some question about calcium that someone was asking, and I don't know what number that is. Let's see if I can find it. Calcium, 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 calcium. Okay. Which atom in the ground state has the same electron configuration as a calcium ion, Ca+2, in the ground state? So, we know calcium's ground state configuration is 2882. If you just joined us, we just did an example a few minutes ago with calcium, but calcium's ground state configuration is 2882. It tells you in the question that it's charged. It tells you in the question that it's charged +2, which means you have 2 more positives than you do negatives. That means you've lost 2 negatives. And those 2 negatives are electrons, which means these 2 electrons go bye-bye, which means you need to find which atom on the periodic table is 288. And you go looking, and you go looking, and boom, argon is 288. So, when you get these ion questions, just keep in mind you are changing the amount of electrons you have. Positive always loses electrons. Negative always gains electrons. So the answer was argon, which for me is answer choice 1. Hopefully that it is for you too. But like I said earlier, these questions are not matching up, so that's just unfortunate. Isotopes. So you're guaranteed every single year to get a question like this one. Something about average atomic mass, which is all about isotopes. So let's talk, generally speaking, what an isotope is. Isotope means you have the same element, I'm just going to say same atom, different mass. Same atom, different mass. Same atom, so the protons are the same. Different mass, neutrons have changed. So since you have the same atom, technically your electrons are also the same. But when you think I have the same atom, your brain should go protons, not electrons. Unless the question asks you to think about electrons. When you hear same atom, you think same protons. So isotope, same atom, different mass. Different mass means your neutrons have changed. Because if your protons changed, you're not the same atom anymore. You're something else. I'm trying to think if there's anything else worth noting. I guess technically this table is not an average atomic mass question. They're just having you draw dot diagrams based on this table, which the table doesn't give you any useful information. But if you get an average atomic mass question, that is not how you think to do it. Don't add up these four masses and then divide it by 4. That should not sound familiar from chemistry. In here, you should take these masses, so you're going to do 31.97, multiply it by 94.93, add that to 32.97, multiplied by 0.76, and you probably see the pattern by now. Mass times percent. Mass times percent. Mass times percent. Add them all up, and at the end, divide them by 100. Take your time. You can't use a graphing calculator tomorrow. You have to use scientific or function or something really basic. So really take your time with these. I think we did not pick, I should say, a particularly long one like this. This one's kind of a pain. But you can't use a graphing calculator tomorrow. You can't use a graphing calculator on the Regents. Don't ask me why. Deal with it. So this is kind of the basic setup. Mass times percent plus mass times percent plus mass times percent, so on and so on, for however many masses and percents you have. Add them up, boom, 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 divided by 100. Some of your teachers might have had you divide these or convert these numbers here to percents initially. Nothing wrong with that. I've even taught it that way. I think this is kind of a fail-safe, easier way, because sometimes students see 0.02 and they're rushing through the test and they're like, oh, that's already a decimal already. I don't have to convert that. You do. So I'm going to move on to the third Castle Learning now and just look over questions there. Shoot me any text on Remind if you want me to go over something else from here, and I'll piggyback to it later. But the third Castle Learning is the big one. That's the bonding one. I think that's for a lot of students, this atomic structure stuff, and the bonding is when chemistry went from like, oh, I'm just plugging these numbers into a formula and doing heating and cooling curves, and then it was like, this is kind of hard. Couple questions I got. Are we going to have to do the x-1 thing? For my Regents students, you probably don't think that sounds familiar. Those of you that are in honors chem, all the honors teachers kind of do that thing. No, you'll never have to do that on a Regents, so don't worry about that x-1 thing. It's 1 minus x, by the way, but don't worry about that. That's not going to pop up. Next one is, when you do a scientific notation on a scientific calculator, is it the number times 10 to the exponent, or is it times e, how it is on a graphing calculator? So if you have a number that is, let's say, you've been doing moles recently. Let's say you have 6.02 times 10 to the 23rd. This expression on your scientific calculator or graphing calculator, you can't do this on a 4 function, but I don't think you can do exponents either. If you go to second function and then like the apostrophe or the comma, somewhere you'll see a big E. If you put in 6.02 big E 23, these are equivalent to each other. And then now this, your calculator will kind of understand in the order of operations versus the one I'm highlighting over here. If you do like x 10 caret 23, it might get confused with the order of operations. So if you have to use a big exponent times 10 to the something, you can just do this. Scientific calculators should be able to do it if you can find it. I don't know if you'll have to do something like that tomorrow, but that's good to keep in mind. Any other, let's see, I got a few other notifications. I bombed the Algebra 2. No, you didn't. Questions on the test. We went over that. Okay. All right, I'm ready to move forward then. Polar and nonpolar. If there's one topic that I tend to just completely hate the most, it's polar and nonpolar. And when I say I hate it, I mean students hate it. Polar and nonpolar bond is not the same thing as a polar and nonpolar molecule. A polar bond simply means two different elements or atoms. So if you have a polar bond, I know some of you, if you are not in my class, are taught to like look at their electronegativity values, and if it's less than 1.7, it's polar. If you have two different elements, it's a polar bond. If you have a metal and a non-metal, it's an ionic bond, which is still extremely polar. But at the end of the day, if the question is asking about polar bonds, that just means you have two different elements. If the question is asking which one is the most polar bond, that's when you have to go to your reference table, go to table S, and look at their electronegativities. So H was involved, Cl was involved, Br was involved, and iodine, which is all the way down here. And whichever bond, when you subtract them, has the largest difference in electronegativity, means it's the most polar. So if I can remember the answer choices, it's probably going to be HCl, because 3.2 minus 2.2 is 1. And I don't think any of the other ones come really even close to that. So when you have a question about polar bonds, it's two different elements. If the question is about which is the most polar, you got to look at their electronegativities on table S, see which one has the largest difference. That one is going to be the most polar. I'm just going to cover polar and nonpolar now. Let's just hit all these questions about polar and nonpolar. Because who likes this? Nobody. Polar molecule is not the same as a polar bond. And when you see polar molecule, your brain should go to SNAP, which stands for the following. It's easier if I say it than write it. So this is an acronym, SNAP. Symmetry, nonpolar. So you have to draw these. Now, answer choices 1, 2, 3, and 4, I know for a fact in my chem class, we've drawn so many times, you should know these in your sleep. But maybe you don't. So take your time when we draw them. We'll draw them all together right now. Don't worry if you've forgotten. But you got to draw it. If it's symmetrical, it is not polar. If it is asymmetrical, which means it does not have symmetry, then it is polar. So it doesn't matter if the bond is polar. You can have a molecule, which one of these will be an example of this. Actually, two of them will be. You can have a molecule that has a polar bond, but as a whole has symmetry and is therefore not polar. So symmetry, not polar, asymmetry, polar. Cole, I'm going to address you directly. The IMF stuff, you have to know very little about IMFs. You have to know they exist, and you need to know hydrogen bonding, and that's about it. So ion dipole, stuff like that, don't worry about. We're going to go over covalent bonding and ionic bonding. Don't worry about that. That's a big topic. I'm just doing all this polar stuff now because that's a pain. So you got to draw these. So I'm going to go over how I go teach my students how we draw things. If any of you who are watching that are not students of mine, I try to simplify it as much as I can. This doesn't work once you get below period 2, but most of the stuff that Regents is going to ask you to draw is basically any diatomic molecule like O2 or N2, H2, carbon dioxide, water, CH4, and NH3. That's pretty much it. So the first one that they wanted you to draw in this problem was O2. So I go to oxygen. I got to figure out how many valence electrons oxygen has. So your valence electrons are the electrons in the last energy level of any atom. So oxygen here has 6. So I'm going to draw one oxygen with its 6 valence electrons. So usually I teach my students north, south, east, west, 12, 3, 6, 9, whatever. Draw one dot at a time before you pair them up. So 1, 2, 3, 4, 5, 6. When I look at this oxygen on its own, I see that it has 2 pairs, or not 2 pairs, but 2 electrons here and here that are open, that are free, that want a friend. And if you pair it up with another oxygen, then that oxygen also has 2 free that would like a friend. So these are going to bond together. Don't make this your final answer if you're ever asked to draw anything. Clean this up, please, and give it some bonds, which are lines. And we have a double bond here. Always double check that each atom has 8 electrons. Don't forget to draw the lone pairs. So I count 2, 4, 6, 8, 2, 4, 6, 8. So we're good. If I look at this molecule as a whole, I think it's pretty clear that oxygen is symmetrical. You have an O here, you have an O there, you can cut it down the middle, it's distributed evenly, it's symmetrical. Also, if the bond is not polar, like this one, O2, it's the same thing bonded to itself. If the bond is not polar, then the molecule is also not polar. So oxygen was not the correct answer. What about, I'm going to draw NH3. If I draw one N, I look it up on the periodic table, N has 5 valence electrons. There's 3 hydrogens bonded to it. I see 3 lonely electrons looking for friends. Give those electrons a friend with hydrogen. Hydrogen does not want 8. Hydrogen is happy with 2. So never, ever draw a lone pair on hydrogen. You're not going to see it. As soon as something is bonded to hydrogen, hydrogen is done. So don't put dots on hydrogen, please. When I look at this molecule, I would say this is not symmetrical. While this side, no, Nick, you don't need to know the shapes of compounds. While this side is symmetrical, I have an H over here, I have an H over there, boom, they cancel each other out. This side is not. Because while I have an H on the bottom, I have a lone pair up here. That gives this no symmetry. Because that lone pair on that nitrogen destroys the symmetry it could have had. If this was an H up at the top, if I had an H coming off the top of nitrogen here, I would say it has symmetry. But I don't see that. And the question wanted to know which one was polar. Well, the one without symmetry is NH3. The end. 6. Which formula represents a nonpolar molecule containing polar bonds? So, do the easy one first. Cross out the answer that doesn't even have a polar bond. Polar bond means two different things. No, that is not two different things. Those are the same. Now you have to look at them and see where there's symmetry. And you're going to somewhat want to be confused because 2, 3, and 4, if you look at the atoms in the middle, none of them have lone pairs on it. But if I look at 3 and 4, those bonds are getting bent. And they're getting bent by something. And whatever's causing that bending means it's not symmetrical anymore. Because there's something going on up here with the oxygen and up here with the nitrogen that is causing the bonds to bend downward and downward and downward. And that means you're not going to have symmetry. Because 3 and 4, there's lone pairs on that N, and there's lone pairs on that O that are causing the bonds to bend. Which causes those shape names, someone asked me about, that you do not need to know for tomorrow. So like tetrahedral and linear and bent and trigonal pyramid, you don't need to know that for tomorrow. You just need to know how to draw shapes and draw atoms and draw ions. And we'll do an example of an ion in a minute because that's a big one. So this one, 3, yes, that's a polar bond, but it's also a polar molecule. Remember the question asked for a nonpolar molecule. So 3 and 4 are out. CO2 is nice and symmetrical. I got a C in the middle. I got an O over here. I got an O over there. It's nice and symmetrical. Nonpolar. Snap. Okay, let's see. We'll do bonding next, and then IMFs, and then I'll take any questions, I guess, because that's pretty much the rest of it. Okay, I want to go over how to draw an ion really quick, and then we'll go to bonding. So, drawing an ion. Let's say you were asked to draw sodium and sulfur. If you were asked to draw sodium, its dot structure, you would look at its valence electrons. It's 2-8-1, and it gets 1 dot. I'll make it bigger. If you were asked to draw sulfur, it's 2-8-6, which means it has 6 dots. So these are atoms. These are not charged. If you were asked to draw Na+, sodium's ion, sodium is charged +1, your final answer would look like this. Done. Because +1 means you lose this electron right here. That's gone. And when that sodium loses that electron, it doesn't have any more valence electrons. All the valence electrons are gone. So it's just sodium. Put the charge. You need to put charges on your ions because ions are charged. If you do not put charges on these, you get no credit. You can put brackets if you want to. I don't really care if you do or don't. That's just not as important as the charge. So, sulfur. Sulfur has a charge of -2. 2 minus means you gain 2 electrons because electrons are negative. So, you need to draw sulfur gaining 2, which you can signify with an X. You can make them all dots. You can do whatever. It doesn't matter as long as you show it has 8 valence electrons because it gained 2. and you put its charge because it's an ion. So just keep that in mind. Bonding, 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 bonding. We'll do 29. As soon as you see this phrase, electrons are transferred, ionic, period. That's what it is. I don't even care that the next thing says metal and nonmetal, which is another hint for ionic bonding. Those are 2 hints for ionic bonding. But as soon as you see electrons are transferred, yeah, we should have extra calculators. Just get a calculator. If you see electrons are transferred, boom, ionic. Every time. So cross out the ones that say, that's not crossing it out. Cross out the ones that say covalent. Because covalent is shared. Covalent's like cooperative, shared. Cross out covalent because that's wrong. The next thing about ionic compounds is they have a very, very high melting point. That's just a fact to know about ionic compounds. If you want to try, go pour some salt in a pot and put it on your stovetop and turn it on and watch it not melt. It has a high melting point. If you put sugar, a lot of it, on your stovetop and turn it on and maybe get some milk and cream, you can make caramel because that sugar is going to melt. That sugar is going to melt. And yes, it's caramel, not caramel. I don't know what is going on or what's wrong with the world with people saying caramel. It's caramel. Where'd the A go? Crazy. 24. Just because it says molecular, I just want to make sure I hit this. Molecular means you're a molecule, and the only substances that are molecules on the planet are nonmetals with nonmetals. Ionic compounds don't form molecules. Ionic bonding leads to crystals. Metallic bonding is... The fact that we can even call it bonding to me sometimes is weird. Metallic bonding is all about those electrons moving everywhere. They don't form molecules. They form a variety of different structures. So when you see molecules, you think covalent. Oh, why do I keep picking the highlighter? You say covalent, because that's what it's asking. Covalent and molecular go hand in hand. So just keep that in mind. More bonding. Bonding, bonding, bonding. Okay, 17. Ionic and covalent bonds. If this was a short answer question that was along the lines of which of these compounds, or what are the 2 types of bonds in this compound, the answer is always going to be ionic and covalent. Because metallic bonding just exists on its own. If you have multiple metals together, you'll have an alloy, which we don't really even talk about. And if you have multiple nonmetals together, all the bonds are covalent. They're not different. You can't have a network solid compound and a covalent compound. So, when you see a question that asks which compound has both ionic bonds and covalent bonds, the trick here is if it says ionic, you know it needs a metal. If it says covalent, you know it needs a nonmetal. And if it has both, you need 2 nonmetals. I'm just going to write 2 non. You need 2 nonmetals because the first metal is going to bond to this ionic covalent, not this ionic covalent compound. Let's start over. The first metal is going to bond ionically to the nonmetals, and then the 2 different nonmetals are going to bond covalently to themselves. So let me clarify that. Not 2 nonmetals, you need 2 different nonmetals. So, ionic, your brain goes metal. Covalent, your brain goes nonmetal. Both, your brain goes metal with 2 different, or more, but 2 different nonmetals. I'm not going to give my PSN name, and we're not playing Fortnite together. You're just going to have to deal with it. This is the correct answer here. And the reason I want to say two different nonmetals, if you see an answer choice like MgCl2, that does not contain both ionic and covalent bonds. That's just ionic because the two chlorines are bonded to the magnesium. The two chlorines are bonded to the magnesium. If you can see some of the questions and things I'm getting, it's just, that's why I'm cracking up. Okay. So there's a lot of questions on here with polar and nonpolar. You can definitely try on your own now, hopefully. I'm going to try to tackle a few more bonding questions. Okay, metallic bonding. Goodness. At STP, which substance has metallic bonding? Pick the metal. Pick the metal. So, let's go to look at the periodic table. Maybe we don't know which ones are metals. The metals, I'm going to color them in, are these. Those are your metals. I didn't color in hydrogen. Do you notice that? Because hydrogen is not metal. So these are your metals. Your metalloids are on the staircase. I'll color them purple. Metalloids. And then anything that is not colored, technically we ignore the bottom, but let me color that in just so we don't get confused. Anything that is not colored, and we ignore the U's too, so I'm just going to color those in. Anything that is not colored is a nonmetal. So if you need to pick something that has metallic bonding, you pick a metal, and just a metal. Because if there's something in it that's not a metal, then it's not metallic bonding because you don't have just a metal. So when you look at the question, pick the metal, which is silver. I don't even know how you could argue with me that it's not silver. Like if you put 2 and you say, but there's a metal in it, I'm like, how does that trump silver? You should know what silver is. It's like 90% of the jewelry you see is silver. So, just keep that in mind. Okay. 8, 9, 11, I think will come up next. Maybe we'll do 2. 2, potassium chloride. STP, what does that mean? So, for most questions, STP just means that you're at standard conditions. So you're at the conditions that scientists try to naturally measure how these things behave. STP, so let's just look at it because it comes up in question 3. STP for this question doesn't really matter. Technically it matters, but for you, it doesn't really matter. All that means is that you're at standard conditions, so nothing funky is going on. STP for a problem that asks you to calculate something is different. So if it's asking you to determine or calculate or something involving this, that's when STP actually makes a difference and you need to look up the value. So in most questions, if there's not a number involved and it's just dealing with properties of things, STP is not really going to make a huge difference. It's just there to let you know it's the technical right way to ask that question. If you're dealing with P1, V1, T1 and STP pops up, that's when you have to go to table A. Double check your units, make sure you're in Kelvin, make sure your pressure units are both the same, so either kPa or ATM. Don't worry about any other pressure units that you might have learned in class. They're not going to pop up. So STP in question 3 here doesn't really matter. In question 3, at STP, let me turn this. At STP, graphite and diamond are two solid forms of carbon. Why do they differ in hardness? This was the question I was talking about. This is asked a bit differently, But this is the question I was talking about in class when I say different things are different. Pick the answer choice that best exemplifies that. And if you're talking about hardness, like how easy it is to break something, they probably differ in their structures. But different things are different. That's just a really easy concept to keep in mind. That'll pop up tomorrow. I can almost guarantee it. So just if you have two different things, they can have similar properties. Don't think, but like, didn't you say, Mr. G, that all the elements in the same group have the same properties because they have the same amount of valence electrons? They can do things similarly, but they're still different. All of us as people, we're all people. That's similar about us. I would argue that I am a vastly different person than all of you, and all of you are vastly different people than each other. But we do similar things because at our core, we're people. So don't confuse similar with same. Different things are, at the end of the day, different. So they have different properties. 2, potassium chloride. Potassium is K. That's probably the only reason they pick potassium for questions like this, because they want you to think it's P. But potassium is K, which makes it a metal, and chlorine is Cl, which makes it a nonmetal, which means we have ourselves an ionic bond here. And ionic bonds transfer electrons. Covalent bonds share. That's why every time you see a covalent bond, like all these, they all have the lines indicating I'm sharing an electron with you. Versus any ionic bond, which I think one is drawn somewhere in here. Ionic bonds have the brackets because Mg is not sharing electrons with F. Mg is giving them away to F, turning it into an ion. So just keep that in mind. IMFs, since that popped up before, at the very least, when you get any question that concerns IMFs, it's just about data. So the stronger the IMF is, the higher the boiling point. So you would argue that HF has the strongest IMFs. For those of you that went a little bit more in depth with IMFs, do not worry about dispersion. Do not worry about dipole-dipole. Do not worry about ion-dipole in the sense that don't worry about a question saying those words. You still need to be able to know how ions interact in water, and we'll go over that in a minute, but don't worry about that term. So the only IMF you need to know by name is hydrogen bonding. And you need to know it because of what you see with the data right here. There is no reason why HF is unusually higher than the other three. Because if you look at the other three, these are all in group 17. Each one of these here are in group 17, F, Cl, Br, and I. And if you look at the data from Cl down, it just goes up at a pretty constant rate. But for whatever reason, HF is much higher than all of them because HF is hydrogen bonding. And hydrogen bonding is Pon. So you need an H with either an F, an O, or an N, and that's hydrogen bonding. So it is just there to explain why stuff like this happens. Why does this data exist? Because the data goes against what you would predict. So that's the only IMF you really need to know. The only other thing you need to know about IMFs is that they explain phases. So they explain why boiling points are so high or so low. So if something is, let's say they're like, you're at STP. And at STP, I know that sulfur is a solid and O2, oxygen, is a gas. You would argue, hopefully, that sulfur has stronger IMFs than oxygen because sulfur is a solid at this temperature while oxygen is a gas. So oxygen is very easy to just pull apart from other oxygens. You're not breaking a bond like in 9. 9 does not show IMFs. 9 is bond breaking. You're taking one oxygen and another oxygen and just separating the molecules apart from each other, not actually taking the bond and breaking it. So you would say oxygen has weaker IMFs because it's a gas. Speaking of 9, if you break things, energy is released. Just kidding. It's absorbed. When you break things, energy is absorbed. I have to put energy in, if I want to break this pen, I have to put energy into the pen to physically break it. So if you see a bond breaking, like here, you see one molecule here, two things over here, you have put in energy into that system and literally broke the bonds apart. Versus if you are forming a bond, so you take number 9 and you go in reverse, they're coming together and you hear that energy of them coming together. Imagine you had magnets and you just hold them really close and let go and they come together. You would hear that energy being released. So bond forming releases energy. Bond breaking absorbs energy. Now, some of you might be clever enough to say, well, Mr. G, if you break a pencil, you're going to hear that too. And that's an argument for another day, because I would say I'm putting more energy into breaking it than the energy you hear coming out of it. But at the end of the day, I think that analogy should work okay. Breaking things absorbs energy. Forming things releases energy. So just keep that in mind. Hint, hint, wink, wink. Let's see, what else is on here? Let me see, make sure I didn't miss anyone's questions, because I got 8 reminds right here, but I know half of them are nonsense. You get a calculator. There's the PlayStation question. Didn't you say you had Xbox? Why are you even asking? I'll go over naming in a minute, just because we did that a little bit yesterday, but that never hurts to go over again. So just hang tight if you're looking for naming. Shapes of the compound. Okay. Coal. How to tell the difference between all the crystalline solids and IMFs. I don't understand the crystalline solids one. But I'm going to take that as telling the difference between the 4 types of bonding and how to look at data and figure out if you have ionic or covalent or something. And then I'll go over ion dipole too. Okay, so properties of compounds. Let's do 22 first. You need to know properties like this. Do they melt at high or low temperatures? Do they conduct electricity? Are they dissolvable in water? Where typically the first 2, conductive and melting and boiling points, are usually all you should need to answer the question. The problem with 22 is, for me at least, I haven't used the term electrolyte yet because honestly it's not an important term to know yet. But electrolyte means it's conductive in water. Think about all the energy drinks, not the energy drinks, like the sport drinks. We have electrolytes in Powerade. You should buy this. Okay. Those electrolytes in there are ions, which are conductive. So if it melts at a high temperature and it's specifically called an electrolyte, which I don't think you'll see that term tomorrow, so don't worry about it, that means it conducts as a liquid. You're looking for an ionic compound because metals don't dissolve in water and covalent compounds don't conduct electricity. So 2 would be your ionic compound. So ionics conduct, but only as a liquid or only when they're dissolved in a liquid. Covalents are low and no. They don't conduct and they have low melting and boiling points. And then metals are super high conductivity, even as a solid, and they have very high melting and boiling points. So we have to keep those straight for tomorrow. So the only one I didn't talk about was, I'm going to scroll down here to get some space. So there's 4 types of bonding. That was almost 5. 4. There's ionic, covalent, metallic, and that weird one called network. And you need to know generally like what they are and then the properties of them. So what they are, we've done ionic, covalent, and metallic already. Ionic is metal and nonmetal. Covalent is nonmetals only. Metallic is metals only. And then network there's like 4 that you just need to know. Diamond, graphite, and then the 2 silicon compounds, silicon carbide and silicon dioxide. Some questions are as easy as like, which one of these substances is a network solid? And you just pick the ones that have silicon in it, or diamond or graphite. But usually they ask about the properties. So the properties, we have melting point and boiling point, which for ionic is going to be high, for covalent is going to be low, and the other 2 is going to be high. So covalent is low and no. Electricity, so I'm going to say conductivity. For ionic, that is a yes, liquid only. I ran out of room, sorry. Yes, only in liquid. So ionics can do it if they are melted or they're in solution, which means they've dissolved, which means AQ. So don't forget that AQ means dissolved. That's a question on one of the Castle learnings. It's like, which one of these is a mixture? Pick the one that says AQ. Covalent is no, metal is yes always, and network is no. So low and no is covalent. High and always no is network. High and sometimes is ionic. And high and always is metallic. Those are the properties. Cole, to get at your question, so I'm going to leave some, again, I'm not doing like all of these because you should, if you just wait for the answers from me, you're not going to gain anything out of this. So I'm leaving some of these open for you to try on your own because I'm not going to be there taking the test for you tomorrow. But, Cole, to answer your question about what ion dipole means, to a lot of people watching this, you probably haven't even heard that word being mentioned before. But ion dipole just means how do ions and water interact with each other. So if you draw water, H2O, and you look up their electronegativities on table S, or you're just really good at memorizing those trends, O is very electronegative compared to H. So O gets that weird looking negative symbol because it's kind of negative, and H gets that weird looking positive symbol, so it's kind of positive relative to O because O is so electronegative, which means it's really trying to take H's electrons away. That if you dissolve an ionic compound in it, like this one, you dissolve that in water, the ions literally start to dissociate from each other, which means move away. And the NH4 pluses are going to be oriented with the oxygen because opposites attract, versus the chlorines are going to be interacting with the hydrogens because, again, opposites attract. So the positives and the negatives like to hang out. The negatives and the positives like to hang out. And when you see a question like 21 here, you want to make sure that the hydrogens, which are the black dots, are interacting with that chlorine correctly. So all the hydrogens need to be facing towards the chlorine and never the oxygens. So 1 is 100% wrong because the oxygens are facing it. 2 is half right. The hydrogens are facing the one on the right, but not facing the one on the left. 4 is the same deal. 2 They don't both need to be oriented towards the chlorine. Remember, these are molecules, and they're moving pretty quickly. But they at least need to be oriented correctly. So you never want to show the oxygen facing the chlorine, because that just doesn't make sense. The only thing I'm not seeing a lot of is periodic table stuff. Which is unfortunate. But in terms of the periodic table, that was like the last quiz we took of the quarter, which ends Friday. So if you're planning on not coming to school, if you're missing a lot of work or you need to get your grade up or do a lab or something, I would highly recommend you come to school Friday. Also, I would highly recommend, because it's the school day, so you should be there. But the periodic table stuff, like ionization energy, electronegativity, stuff like that, you can look up ionization energy, electronegativity, and radius on the periodic table every time. You will never be asked about multiple ionization energies or the crazy stuff a lot of my kids in my third block have been seeing on the periodic table quiz that they didn't like very much because it was so hard. 1, get used to that. But 2, don't worry about that for the Regents or tomorrow. What I would be concerned with is that you understand the trends from left to right and up and down in terms of why they happen. So in terms of the trends, when you go left to right, for any of the trends, so the trends are, again, ionization energy, electronegativity, and atomic radius. I don't care which one it's asking about. If they're asking you to explain it, and you're going left to right, it's because you're increasing the amount of protons you have. If you want to have an even better answer, it's increasing the amount of protons, and the electrons are in the same energy levels. I'll just say in the same level, or shell. That is the correct answer for why any trend exists left to right. It doesn't matter what the trend is. The really good answers, like you'll get in AP Chem, are talking about nuclear charge and stuff like that. But in terms of this class, that's all I'm looking for. So you notice the protons are increasing. Even better is if you mention the electrons are staying in the same place. That's an awesome answer. But I really, really just want you to tell me that the protons are increasing, which means the nuclear charge is increasing. As you're going down, so the trend going down, I think is even easier. I'm going to make it a different color. The trend going down, different color, blue. It's because the electrons are in higher energy levels. And that's true for any trend going down. Why is the atomic radius doing this going down? The electrons are further away. Why is the ionization energy going down? The electrons are further away. Why is the electronegativity going down? The electrons are further away. In terms of ionic radius, so ionic radius is not on... negative ions are bigger because you're gaining electrons and the protons are staying the same. Again, if you throw in the protons are the same, that's awesome. If not, at least I want you to conceptualize that gaining electrons makes you bigger. The positive ions are smaller. This one requires a bit extra work because you lose an energy level. Sorry, my handwriting's awful. Or shell, however you want to word it. And you have to say that. You can't just say you're losing electrons because that's a poor answer. And really, if you're losing electrons, if you want to say you're just losing electrons, you have to talk about the protons too. A lot of times short answer questions will kind of hint at this and say, explain in terms of electron shells why the atom gets smaller. So just say you lose electron shells. Use the darn terms for those stupid in terms of questions. That is so frustrating. Every single year, some kid writes a beautiful answer but just says it. or doesn't use the terms and answers it in a different way, and you just can't give you, I can't give you credit. The terms are a hint. It's telling you you should talk about this, so talk about it. People are still going to forget. That's life. It's okay, though. I'll take more questions on here. I'm going to get back to the first question from way back, which was naming and formula writing. Grace, I didn't forget you. And go over that. That's it. I'm doing for the CASA learning, and that's kind of it for general review off my head. So if you don't have any questions for me, go get some sleep. Do the CASA learnings that are due tomorrow that I assigned like 3 weeks ago that you've been putting off because you're all excellent procrastinators. It's worth 30 points. It's like an easy 30 points. It's such an easy way to get some points into your grades to help you. So just get them done. If you run out of time, just keep in mind, if you don't get them done by tomorrow, you're not going to get a 0 if you turn it in late. But the quarter ends soon, so try to finish it. Formula writing and naming. Those prefixes, I'm going to say not worry about too much because they have been less and less and less popular to the point where I don't even know if they're in the curriculum anymore, which is kind of weird because you call carbon dioxide for a reason. So I'm just going to go over the charges and crisscrossing and all that fun stuff, and then hopefully you'll be okay. So I'm going to do name to formula first because I think that's harder. Usually. We'll see. Sodium oxide versus copper 1 oxide. Both of them are going to use the same principle to get to the correct answer. They just look a bit different. So first of all, why does sodium not have a Roman numeral associated with it, but copper does? If you look at the reference table, at the periodic table, you will notice that, oh God, what a mess this is. You will notice that sodium is always, sodium is Na, by the way, always +1. So you don't need to say sodium 1 oxide because it's always sodium 1 whatever, sodium 1 nitrate, sodium 1 sulfide, sodium 1 carbonate. It doesn't matter what sodium's charge is. Well, I shouldn't say that. You don't have to label sodium's charge in the name because it's always the same, so don't be redundant. So copper, though, which is Cu, has 2 choices for charges. So you need to indicate which copper do you have, because copper 1 oxide and copper 2 oxide are both, though at a glance look very similar, are 2 totally different compounds with 2 totally different properties because different things are different. So that's why sodium doesn't have the Roman numeral, because sodium is always +1. Write down sodium with its charge. Write down oxygen with its charge. And look at it. And say to yourself, those don't balance. They're not the same charge. You can't have a compound where the charges don't balance each other. It's just, it doesn't exist. So you're going to use the trick of crisscrossing. Bring the 2 across and down, bring the 1 across and down, and you get the formula Na2O. Copper 1 oxide, you're going to do the same thing. But you don't really need to look at the periodic table for copper, unless you forget its symbol, because I tell you that copper is +1, because it says copper 1. How was meeting 8th graders?
Good.
Yeah?
They were cute.
Are they excited to come to high school?
Not really.
Not really, no.
But they were cute.
Did they say anything?
They're just 8th graders. They're goofy.
Mrs. G just got home. So
Hi, guys.
she said hi. Anywho. Copper 1, and then oxygen is -2 like before. So it's the same thing that we just did. Crisscross the charges. Cu2O. Copper 1 does not mean you have 1 copper. It's the mistake I see all the time. And chances are you're probably the student that doesn't make those mistakes that's watching this video. And the students that do make those mistakes aren't watching. They're going to make this mistake tomorrow. I guarantee it. So, don't make that mistake. It's the charge. Let's do a table E one. Let's do nickel 2 phosphate. Fun. Okay, so if it ends in TE, it's from table E. Period. If it ends in DE, chances are it's just an element because the naming convention is take the nonmetal, drop the ending, add IDE to it. The only exceptions are like peroxide, hydroxide, and cyanide. And cyanide and peroxide should set off a little alarm in your head that these don't sound like elements to me. This is probably from TE or table E. Hydroxide might confuse you a little bit. You might think it's hydrogen, but hydrogen is hydride. Hydroxide's OH minus. And you'll typically avoid mistakes with hydroxide because when we get to the acid-base unit, you'll learn about what hydroxides are. Harper, you want to come say hi again? Come here. Want to say hi? Want to say hi? Nope. Okay. Oh, maybe. She'll show you her tail. Hi. Go say hi. Who are these people? You can't see them. You're like, what are you talking about? Can you let me out? Give me a treat or something? Go find Mrs. G. So, nickel 2 phosphate.
You're just cracking yourself up.
Me? Well, yeah. I've been doing this for over an hour, so, you know.
Okay.
The silliness gets exponentially higher. Stop interrupting, Mrs. G. Mrs. G. Nickel +2, because it's 2 with the Roman numerals. Phosphate, table E, TE, table E. Find phosphate. First find table E. Goodness. Find phosphate. Phosphate's PO4 3-. Put that thing in parentheses. Put the PO4 in parentheses. Just so you don't get confused. And then put the charge on the outside. Because I don't want you to start distributing the charge by accident with the 4. So just parentheses. Crisscross applesauce. And you get, I say that in class. And you get Ni3 PO4 dose. And that's a crash course in naming and formula writing. When you name things, just always remember the metal never changes. If you have nickel, you have nickel. If you have sodium, you have sodium. If you have cadmium, you have cadmium. If the metal, when you look it up on the periodic table, has more than one charge, indicate the charge in parentheses. And then the non-metal, if it's a non-metal and there's just one of them, you change the ending to "ide." And if it's from table E, don't change the ending at all. Just keep it the way it is. I'm going to wait about 30 seconds to a minute. See if you got any more questions. It's been a while since I've gotten some notifications, but I'll wait about 30 seconds. I hope this was, at the very least, a little bit helpful. Get those castle learnings done. You're going to do fine tomorrow. I think it's very doable. I think it's very doable midterm tomorrow. I'm not saying it's easy to get 100, because I don't think any chemistry test for anyone would say that 100 I got was really easy. But it's very fair and it's very doable. They keep asking me to stream Fortnite on the PlayStation.
No.
Yeah. It's okay. They're going to try.
You know you can see how many kids are still watching, right?
Yeah, I know.
Okay.
But ignored
like the
that.
mystery?
I like the mystery. Where would does it say in the dashboard? Or do I have
If
to...
you go to the actual YouTube live.
Yeah, that's what I figured. I wasn't sure if there was an easy way. It says 14 watching now. My first one got like 80 views, so you know, I think I'm going places. I should probably contact YouTube and try to get some ad money. You know? Yeah.
Are you still streaming?
Yeah.
You're just cramping yourself up.
Kinda.
Yeah.
Then I'd give them like a minute, see if there's more questions. I'm leaning towards no, but you know, some people are slow typers. They're funny. Students are hilarious. All right, I think that's it. Actually, someone just joined too. It's so funny. Have a good night, guys. I'll see you tomorrow. I'll be in there. You need a good old-fashioned, regular scientific calculator and not a fancy graphing one. Okay? Have a good night. I'm not getting you Roma. You know what? This makes me want to go get Roma now and just eat it as you're taking your test. Yeah, you're not getting Roma, Spencer. Good night.